second lecture of this series. Dr. Aswin is going to continue with this lecture for next.
All right. So a brief recap of what we were doing yesterday. We to define to get into the host of dimension, we started with the definition of a host of measure, right? And we used Theodori's construction to define um, the S-dimensional host of measure of a set A in RD to be the limit of the S-dimensional uh, delta content of A, where the S-dimensional delta content, or the host of content, is defined to be the infimum over all over the sums of S power of the diameter of, where these EIs cover A, and their individual diameters are bounded above by delta. So, in other words, the S-dimensional host of measure was defined by considering these sums of small covers of A, right? Now, today we plan to start by looking at or by defining host of dimension, and we do that by inspecting the value of the S-dimensional host of measure for varying exponents of S. Okay. So it's easy to see this theorem. So for I don't know what I'm doing wrong this time, but this screeching noise is really annoying. So this is saying that if you have two exponents s and t, where s is strictly smaller than t, yeah, and if the set A has finite s-dimensional host of measure, then the t-dimensional host of measure of A must be 0. Okay, or equivalently, I can say that whenever host of measure of the t-dimensional host of measure of A is positive, the s-dimensional host of measure of A must be infinity. Okay. The proof is very simple. We just have to follow the first principles. So take a positive delta, and let's cover A with sets, say EJ, where each EJ is small, its diameter is at most delta. And I'm also going to assume that this cover is chosen in such a manner that the sum of the S power of the diameters of these EJs is in fact bounded above by the S-dimensional delta content of A plus 1. I mean, from the definition, I can assume I can find a cover satisfying this property. Right? Remember, we are under the assumption that the S-dimensional Hausdorff measure of A is finite. Okay. So now, if I look at uh, the the teeth sum, right, where I simply compute the teeth power of diameter of edges, then this is bounded above by, see, each diameter is anyway, I mean, for each j, diameter of each is bounded above by delta. So I can pull out delta per t minus s, and then I'm left with this guy, and that's bounded above by delta per t minus s uh, times some finite quantity. So let me just put a wiggle over there. And now I see that as delta goes to 0, I mean, okay, so there's one more step, right? So from this, I immediately see that the T content of A is the infimum over all such sums. And here we have chosen one particular cover. So this is bounded above by some constant times delta power T minus S. Yeah. And now as delta goes to 0, you can see that the t-dimensional Hausdorff measure of A is in fact 0. So as an immediate corollary of this theorem, I can also see that whenever A is a union of AJs, countable union of AJs with the S-dimensional Hausdorff measure of each AJ is finite. Okay. I mean, I don't want like I'm not expecting a uniform bound here. I mean, for each j, as long as the S-dimensional Hausdorff measure of AJ is finite, I'm okay with this. Okay. Then the t-dimensional Hausdorff measure of A must be 0 as well uh, for any t strictly bigger than S. Yeah. So you see that this follows from this theorem because since AJ has finite S-dimensional Hausdorff measure, from the theorem, I see that the t-dimensional Hausdorff measure of AJ is 0. And we have seen that the Hausdorff measure is, of course, as an outer measure. So you can use countable subadditivity to show that the t-dimensional Hausdorff measure of A must be 0 as well. Yeah. Now, as a consequence of this corollary, yes, that's right. If we, uh, I mean, technically, I'm only using. Um, yeah, I know. I can repeat the question. The question was whether we need A to be Borel in this case. So I'm only using the countable subadditivity here, right? So even if A is not Borel, we should be okay. Yeah. So okay. So as an immediate consequence of this corollary, we see that uh, if I compute the t-dimensional Hausdorff measure of RD, then this is 0 whenever t is strictly bigger than d. Yeah. because the d-dimensional host of measure we have seen is a multiple of the d-dimensional Lebesgue measure. Yeah, and therefore it's sigma finite. Yeah, and therefore I can write RD as a union of, I mean, okay, so since it's sigma finite, we see that this corollary can be applied with S equal to D, and by applying the corollary, I see that this is true. Yeah, and consequently, I also see that, I take any subset of RD, the t-dimensional host of measure of that set must also be 0 as long as T is strictly bigger than D. Yeah. So So let me now plot the value of, start with an arbitrary subset of RD, and I'm going to plot the value of the S-dimensional Hausdorff measure of A as S varies. Okay. So we, if you recall, when S equal to 0, we have seen that it's actually the counting measure. The Hausdorff measure is the counting measure. This is S, and this is HS of A. Okay, so where A is, as I said, A is an arbitrary subset of RD. Now, of course, if A is finite, then at S equal to 0, you're going to have a finite value, right? But I mean, we are generally, I mean, okay, so it can be either finite or infinite, okay? I mean, just for the sake of drawing a graph here, I'm going to assume that it's actually infinity, okay? So if I'm starting with an uncountable set, then sorry, if I'm starting with an infinite set, then the zeroth Hausdorff measure is going to be infinity. And for S, you know, I mean, when I move S away from 0, it may remain at infinity for some time. And then there might be a point after which it has to be 0. I mean, I know for a fact that when S is bigger than D, it definitely takes the value 0, right? So it's possible that for some S smaller than D, the S dimensional Hausdorff pressure is also 0. Yeah, I don't know. But there's definitely this jump. There's some, say, SA, at which point the S dimensional Hausdorff measure jumps from infinity to 0. Yeah. At this critical point, what is going to be the S-dimensional measure of the set? We don't know. Okay, but we will talk about that in a while. But the importance of this guy is that this is the Hausdorff dimension of the set. Yeah. So the exponent SA at which the S-dimensional Hausdorff measure of A uh, jumps from infinity to 0 is the Hausdorff dimension of A. Okay. So, I mean, by working with full dimensional objects, you can see why you have defined the dimension in this fashion. If I'm starting with, we have already talked about this last time, right? If I'm looking at a two-dimensional object, if I'm basically measuring its length, using the one-dimensional measure, it's going to be infinity. And if I'm measuring the volume of a two-dimensional object, it's going to be 0. So, uh, you know, the notion that the actual dimension of the object is related to a particular measure, that can aptly describe the size of the set, uh, comes from such examples of full dimensional objects, right? So that's the intuition that we are using here, and this is the definition of the Hausdorff dimension. Do we have any questions? Yes.
No, just out of curiosity, what is the
Yeah.
value of the Hausdorff measure at this critical point for the Cantor set, for example?
For the Cantor set, it's actually 1. I
Okay.
mean, yes.
Okay.
So, I mean, this is the first thing I'm going to prove now. We will see, as I said before, our goal is to look at techniques which allow you to compute the Hausdorff dimension of special certain sets, right? And we'll see that in the case of the Cantor set, the construction can be used to explicitly find out what is going to be the value of the Hausdorff measure at the critical point. I mean, which is going to be log 2 by log 3 if I'm talking
Yeah.
about the middle third Cantor set. Yes.
Yeah. Thank you.
Yes, for any countable set, it's 0. Sorry. Just a second. Are there uncountable sets for which what is 0? That yes, there are sets. Um, to give you an example, uh, I mean, this is way beyond my understanding, but this is collection of, is it Liouville numbers? Yeah, I think it's an uncountable set, but its dimension is 0. Yeah. Okay. Right. So the question of what happens, I can partially, in fact, we can look at some of the easy examples to understand what can happen at the critical exponent. Okay. So let's take, all right, I guess that's not a question. Yeah, I mean, formally, I can also write this down in this fashion. Dimension of A is the supremum over all S such that HS of A is infinity. It's also the infimum over all S such that HS of A is 0. Okay. What happens at the critical endpoint? You can have cases where the S dimensional Hausdorff measure of A, when S is the Hausdorff dimension of A, is infinity. Can anyone tell me an example? RD, exactly. So take A to be RD. The dimension of A is D, and the HD of RD is infinity. Can it be 0? Can you think of an example where HS of A is 0? It's okay if you can't. Well, I'm going to show this. Sorry? Sorry? Yes. That's correct. That's correct. Yeah. I can take. Sorry? Yes. But that's an example. I can take an A to B empty set, and then you can see that it has to be of 0 dimension. But so we will see that for any um, S between 0 and 1, I can find a CS, a Cantor set, a set that is coming out of a construction that is similar to that of the Cantor set, CS in R, such that the dimension of this Cantor set uh, is S. Okay. Now I can define C to be, say, the union of C, what do I want? C1 minus 1 by K. Yeah. So if I take the union of all these guys, I mean, this is something we have to check whether dimension is stable under, countable unions. I'm going to write that down as a property later. But if I take C in this fashion, then you can check that its dimension is actually going to be 1, but its d-dimensional is the one-dimensional host of measure is actually going to be 0. Okay, I mean that's because if I mean for each C1 minus 1 by k, the their one-dimensional measure is actually 0, right? Because 1 is bigger than 1 minus 1 by k. And so for by countable additivity, you get that you get the same estimate for C as well. Okay. I mean, no, it's a union of all these guys. Yes, it is. Yes, it is a candle-like construction. That's right. Yes, we will see this construction probably either today or tomorrow. I mean, in the next class. You have a question? Yeah.
There is a jump point,
Yes.
but however, at that point of jump,
Yeah.
it need not be finite, right?
It need not be finite, but if it is finite, these sets are of special interest. They are called S sets. So yeah, I'm just going to write that down as the. If I take any bounded set in RD, right? I mean, say a ball or something in RD, then you can see that it's going to have the d-dimensional house of measure to be, I mean, finite. Yeah. So such sets, if if HSA of A is finite, if it's positive and finite, then A is called an S set or SA set in this case. Okay, well, okay, why do I even have to mention this? If this is the case, then naturally S must be the dimension of the set. Yeah. So yes, so these sets are certainly of special interest because um, you know we people talk about they study the structure of these sets, and we try to find out density estimates for these sets. So there is this whole theory surrounding S sets. We will not venture into that. If you're interested, you can read about them. Yes, it's there in Matilda. It's also there in Faulkner's book, Geometry of Fractal Sets. Yeah. Yeah. Now, see, being a harmonic analyst, I cannot resist myself from doing this. Now, one another important example of a set that has full dimension, but that can have zero measure, is the Kakeya set. Now, a Kakeya set is a set in RD that contains a unit line segment in every direction. Okay, and it's a conjecture, of course, for all values of D. Whether so, it's known that you can construct a Kakeya set that has measure 0, but what is not known is whether it has full dimension, and it is conjecture that it has full dimension. Very recently, like 2 weeks ago, a pair has they've proved that in D equal to 3, it has full dimension. It's a big result, like a really big result. Um, this is Joshua Zal and Hong Wang. I'm sorry.
Set C,
Yes, yes, yes.
yeah,
Yes,
has one dimension.
this has one-dimensional 0. Yes. Okay. So yeah, a few more remarks. Now, see this. You can see that to identify the dimension. Earlier we had already also looked at few other variants of the host of measure. We looked at the spherical host of measure, for example, right? Where in the definition of the host of measure, you were not. I mean, instead of looking at arbitrary covers, you were looking at covers formed by balls. Yeah, and the measure that you obtained were the S-dimensional spherical measure. And we had seen that the S-dimensional spherical measure is related to the S-dimensional Hausdorff measure. They are just, a constant away from each other. Yeah. So you can identify the Hausdorff dimension using the S-dimensional spherical measure as well. Okay. It's exactly the same definition, except that, HS must be replaced with SS now, where SS is the S-dimensional spherical Hausdorff measure. Yeah. And another characterization or another way to identify the dimension without even going into these uh, into the S-dimensional Hausdorff measure uh, is this observation. So I'm going to write this down as a lemma for A in RD. The following are equivalent. One, the S-dimensional Hausdorff measure is 0. The S-dimensional delta content of A is 0 for all delta. And 3, for any epsilon, uh, A can be covered by sets Ui such that the sum of diameter of Ui to the power S is smaller than epsilon. So it's an easy, I'm going to write this as another exercise. So proof exercise. Yes, that's okay because, this holds for any delta. Yeah. Exercise. So in view of the third item, you see that I could have actually identified, the dimension, uh, I mean, without even getting into measures. Okay, so here you have a much, you could say a better description of, what are the sets that can have zero S-dimensional Hausdorff measure. But, when it comes to actual computations, of course, it's much more easier to work with these definitions. Of course, Hausdorff measures are the way to find the Hausdorff dimension. Okay. Right. Any questions? Okay. I'm sorry. I'm saying if these are all equivalent statements, so yeah, for all delta. Yeah. That should be clear from one, right? Because this is a supremum. Yeah. Yeah. Yes.
Sheri, you are saying that we are saying epsilon and delta, that we have.
No, see, I have not put any constraints on delta. Delta doesn't play any role here in this statement. I'm just saying that for any epsilon, I can cover A by these sets Ui such that the sum of the S power of their diameter is at most epsilon. No, in this, no. I'm not putting any constraint on the diameter of Ui. Yes, but I see, as I've said, like in this statement, there is no delta, right? I mean,
Oh, yes,
no.
I thought that delta. Ah,
Yeah.
oh,
Yeah, no, I can see why you're confused, but no, there's no, yeah. All right. So let's now list some of the basic properties of the Hausdorff dimension. First one is that it's monotone. So whenever A is a subset of B, dimension of A is smaller than dimension of B. Two, it's stable under countable union. So if A is a union of AIs, then dimension of A is the supremum of the host of dimension of AIs. And as a consequence, we see that any countable set has zero host of dimension. Yeah. And third, Lipschitz maps cannot increase dimension. So that is, if I take phi from RD to RD, a C-Lipschitz map, then yesterday we found out the um, we related the estimational cost of measure of the image of a set under this map phi, right? So we had seen that the S-dimensional host of measure of phi of A is bounded above by, I guess, C per S times the S-dimensional host of measure of A. And consequently, the dimension, the host of dimension of phi of A must be smaller than the host of dimension of A. So if I'm taking, if phi is bi-Lipschitz, in other words, if I also have a lower bound, say something like C1 times absolute value of x minus y, then the dimension of the image of A under phi is same as the dimension of A. Yeah. So in this case, so we see that how homeomorphism work for topological spaces. We have the Bilipschitz maps here that are preserving the dimension of sets. And one, I mean, important example of a Lipschitz map is a projection map.
Do you mean by bi-Lipschitz maps?
Okay, sorry. So here, phi is bi-Lipschitz if there exists, say, C1 and C2, such that so you have both a lower bound and upper bound. Okay. . Right. You see that the projection is a Lipschitz map, and this allows you to compute the projection, or at least give an estimate on the dimension of projections of sets as well. Okay. Okay. How am I doing with time? Now, in this class of fractal dimensions, host of dimension is not alone. There are various other kinds of dimensions. There's something called the Minkowski dimension, which is same as the box counting dimension. There's something called the Assault dimension. There's something called the packing dimension. Now, I will not, I was thinking maybe I can talk a bit about the Minkowski dimension, but I think I'm kind of running out of time. So maybe if I have time at the end, I will get into that. But maybe I can just define the Minkowski dimension. So some other dimensions. So you see that you are using various kinds of intuitions that you can draw from full dimensional objects to talk about the dimension of the of the set. Okay. So in the case of Minkowski dimension, you are using. I mean, you are using this idea that if I start with, if I start with um, a full dimensional object, then the suppose I want to cover this set by small balls, say delta balls. Okay. If I'm starting with a say a two-dimensional figure, then you will roughly need delta power minus too many balls to cover it. On the other hand, on the other hand, if I was working with a line, then you only need delta power minus one many balls to cover it, right? So it's this the count of how many how many balls you require to cover a set can be used to define its dimension as well. So this is what's being used to define the Minkowski dimension. So for a bounded set, F in RD, we define NF delta to be the minimum number of sets you require to cover F with their diameter can be as large as delta. Okay. Now we define the lower box counting dimension to be the lim inf of the log of NF delta divided by log of delta inverse. So yeah, and similarly, we define the upper box counting dimension to be the lim sup of these ratios. If these two guys are the same, then you call it the box counting dimension. Then we write the box counting dimension of F uh, as the common value of these two guys. It's also called the Minkowski dimension. Okay, so that's another way to define a dimension for a set. Now there are certain advantages of working with this definition. In particular, I think for practical purposes, it's much more easier to compute these numbers rather than computing rather than computing the Hausdorff dimension through the Hausdorff measure. Okay, but there are, I mean, it has certain drawbacks as well. In particular, you can actually show that this dimension is not stable under countable union. It's actually stable under finite unions, but not under countable unions. In particular, if I take the Z0, 0, 1, 2, 3, sorry, 0, 1 by 2, 1 by 3, all the way up to, yeah, all the way up to 1 by n, then that set has a Minkowski dimension of half. It's a countable set, so you expect it to have dimension 0, but unfortunately, that's not the case. Okay. So I'll just mention this exercise here, and I'll stop this detour into Minkowski dimension. So is that take this set F and uh, the show that the Minkowski dimension or the box counting dimension is actually half. Okay, so it gives you some such anomalies or things that you wouldn't expect. The general relation between the Hausdorff dimension and the Minkowski dimension is that the Hausdorff dimension is always smaller than or equal to the lower box counting dimension, and this is always bounded above by the upper uh, box counting dimension. And you can actually consider examples where each of these inequalities are strict. Yeah, I mean, for the first one, you can use this one as an example because you have a countable set, and we know that its total dimension is 0, but its box counting dimension is half. And there's also another example for this. I think you can find that in, if I'm not wrong, Matilda's geometry of, sorry. No, I'll give you the reference later. I forgot the name of the book. Anyway, so these inequalities are strict as well. Okay. All right. So now what I want to do now is that I want to look at the construction of the middle third Cantor set, and I want to compute its dimension. Okay. Yes.
So you were saying, for example, for a two-dimensional object, you might, I mean, set you would cover it with delta to the minus two balls. So is delta to the minus two meant to be, I mean, or delta to the minus dimension
Yeah.
meant to be the amount of measure per ball?
The amount of
Measure per ball.
I didn't catch that. The amount of
Measure per ball.
amount of measure per ball.
Yeah. As in,
I don't think I quite understand that question.
okay. Maybe I'll formulate
Yes,
it
yes,
better.
yes, 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 yes. But I mean, you see why it should be delta bar minus 2, right? Yeah, okay. Yeah. Right. So techniques for computing, or calculating host of dimension. Let's take our very familiar middle third Cantor set. Okay. So let's just recall its constructions. We had E0 to be 0 comma 1, and EJ is constructed by, or EJ is the union of 2 power j many intervals of length 3 power minus j. And I'm going to call these intervals net intervals, okay, because they have a net property, right, over different scales. So let me call this guy 2 power j net intervals of length 3 power minus j. And of course, the intervals at the jth level is obtained by, removing the middle third portion of the intervals in the j minus 1th level. Yeah. And these sequence, they form a nested sequence of interval sets. And E, our Cantor set, is the intersection of all these sets, right? We are going to show that the Hausdorff dimension of this set is log 2 by log 3. And furthermore, the S-dimensional Hausdorff measure of this set is actually equal to 1 when S is log 2 by log 3. Okay. So typically when it comes to these computations, whenever you're trying to find out, dimension of a Hausdorff dimension of a set, it's the lower bound that's going to create an issue. I mean, it's always, almost always very immediate to see that the dimension of the set is bounded above by a particular quantity. Okay. And you can see that in this case, if we see that E is covered by these net intervals at the level EJ, right? In fact, let me give a name for these, or a name for the collection of these net intervals at the jth level. So let me write. Yeah, I'll just go there so that you don't have to move the camera. Covered by intervals, net intervals of length, and I will say I, coming from curly ij, where curly ij is this whole collection of 3 power, this whole collection of 2 power j many intervals of length 3 power minus j. Okay. Hmm. And length of, so if I compute the s dimensional, where s is this exponent, okay, the critical exponent, um, delta content, where delta is say 3 power minus j of a, then I can use this cover in computing this guy, right? In particular, it's bounded above by um, the size of ij times the diameter of I per s, where I is basically any element in this collection which we have known is of length 3 per minus j. So this is bounded above by 3 per minus js times the total size of ij, right? And that's 2 per j times 3 per minus js. But then since s is log 2 by log 3, you can see that this is exactly 1. Yeah. So that tells you that, okay, so for any j, the s-dimensional 3 per minus j content of A is bounded above by 1. And as j goes to infinity, you can see that the s-dimensional house of measure of A must be bounded above by 1. Yeah. Okay. Now comes the hard part, the lower bound. So I mean, the trouble here, whenever whenever we have to obtain a lower bound for the host of measure, you have to consider arbitrary covers, right? I mean, an upper bound can be obtained by choosing, a really nice cover. In this case, the cover formed by the net intervals. But to obtain a lower bound, since we are taking the infimum over all covers, I should be able to find a way in which you can compare an arbitrary cover with something that I am more familiar to work with. In this case, the cover formed by the net intervals. So what we are going to do now is that we'll start with an arbitrary cover for the set A, and we will try to somehow refine this cover or modify this cover so that we can compare that cover with the cover of net intervals. Okay. So take, let E be covered by this collection, say uh, I, or should I use J maybe? I think that's, no, then I'll forget the notation later on. Um, and we plan to show that 1 is bounded above by the diameter of I, which is simply the length of I to the power s, where I comes from curly I. Sorry, script J. Yeah. An arbitrary cover. Yeah. So maybe by slightly, you know, modify, slightly sort of expanding these eyes, I can, and since S E is already known to be compact, I can assume that this collection is finite. Okay, so it's the first reduction I'm going to make. now let me also assume that all these intervals are also closed. So we plan to, as I said, we plan to refine this cover using net intervals from the construction of it. Okay. To do that, let me choose I to be the or to be a smallest interval in the collection J uh, that contains a pair of net intervals J and J prime. So, I mean, it can look something like this. So I'm only drawing one part of the canter set, okay? So say, so that's the third level. And so let me, for example, take I to be, or yeah, I to be something like this. Uh, yeah. And maybe I can draw something larger here. So the idea is that this I will contain, so that's my I, and this guy contains, it contains many net intervals. In particular, it contains this one and this one. So that's a pair of J and J prime I can work with. I mean, I could have also worked with these two, okay? But so I choose an I in this collection that is the smallest of length, such that it contains two net intervals J and J prime. And these J and J prime, they don't have to be of same length, as you can see over here. For the selected I, choose J and J prime to be the pair, or to be the largest pair of net intervals. Contained in I. Okay. So in this case, as I was saying, I mean, I will not choose this and this as J J prime. I would go for the largest one that is contained inside I, which is this J. And in the case of J prime, I'll choose this one as J prime. Okay. So in this scenario, if I make my choice in this fashion, by perhaps by cutting a piece of I if necessary, I can write I as the union of J with some open set K and J prime, where K is a subset of the complement of the Cantor set, and its length is in fact larger than or is as small as J and J prime. Okay, so in this case, K is going to be this interval, this open interval. Okay. Yes. Not necessarily at the same level. So which is why, as you can see here, I am choosing the largest pair of net intervals. So in this, yes. Yeah. Okay. So yeah. So in this, once you make these choices, as I was saying, if you by cutting down a piece of I if necessary, I can assume that I is of this particular form, right? Now I want to compute the s power of the diameter of I. Okay. So by the s power of the diameter of I is nothing but, I mean, since it's a disjoint union, it's nothing but j plus k plus j prime to the power s. But since the size of k is larger than these two, this is bounded up below by 3 by 2 times j plus j prime whole power s. And now I see that 3 power s is, since s is log 2 by log 3, 3 power s is simply 2. So I can pull out 2 out of this. And then I have 1 by 2 times j plus j prime to the power s. S is strictly smaller than 1. So I can use the concavity of this function to show that this is smaller than j power s plus j prime power s. Yeah. So if I modify the collection by replacing I with this pair j and j prime, you see that the sum of the s power of diameters is not increasing, right? So I'm going to refine the collection in this fashion. I mean, not refine, like modify. So defining I prime or curly I prime to be curly I minus this set, this interval I union j and j prime. We see that the the s what do you the s sum, let me call the s sum uh, among over the I prime collection is smaller than the s sum over the curly I collection.
Time prime here.
Yeah. Okay. And this is because of this inequality. Yeah. So now I repeat this process. Okay. If I can do this one time, of course, I can do it repeatedly. Each time, so I mean, okay, this time I have replaced one interval in this arbitrary collection with two net intervals without increasing the S sum. Yeah. Now I'll look at all the other arbitrary, I mean, elements of this arbitrary cover and then see, you choose the smallest interval in that collection, in that sub collection, and then you choose j and j prime corresponding to that interval, and then you do the same argument, and you see that, by doing this repeatedly, I'll be able to replace this entire collection curly I with a new collection which consists completely of net intervals. Yeah. Whose S sum is going to be smaller than the S sum of over the collection curly I. Is this clear? Right. When do you want to wrap up?
Smart j plus smart j prime power s. So far, so good.
Yes.
That is equal to twice.
Because S is log 2 by log 3. So 3 per S is 2. So, yeah, so after finitely many, by running this algorithm, I mean, should I write down the algorithm? But I think that's clear by now, right? I mean, what I'm doing here. So, by running this algorithm, I can replace curly I with, say, like curly in, which consists of just net intervals. But the S sum over curly in is a lower bound to the S sum over curly I. Okay. So now the thing is, if I'm looking at the members of curly in, it has net intervals, but they may not be of the same length. Yeah. But I can still, I can still refine this collection. I can, I start with, I mean, see, it's a finite collection at the end of the day. So I look for the smallest net interval inside the collection curly an, and then you try to, you replace the larger net intervals with their children successively, so that finally I have a collection that consists simply of net intervals of the same level, of the same length. Is this clear? Yeah. And I mean, I can do that without disturbing the sum, because you're doing the same argument again, right? Yes, you have a question. Yes. Yeah. So so by further replacing the net intervals with smaller net intervals, I mean, for example, if my curly in simply consists of these two intervals, right? Then what am I going to do? I'm going to replace j with, say, j1 and j2. Okay. And you can see that the sum of the sth power of the size of j1 plus the sth power of the size of j2 is exactly equal to the sth power of j. Okay. So, I mean, here you have an inequality, but in that special case, it's going to be an equality. So, by doing this successively, I can assume that curly in consists of net intervals all coming from a single scale. say 3 power minus j. Okay, for a fixed j. But now the thing is, um, the sum of the s the power of so see, even when I'm replacing the even when I'm modifying the collection, I still am left with the cover for the Gantt set, right? So the final cover that we've obtained is basically all the net intervals at the jth level, right? So now the sum of the s power of I, where I varies over uh, in. Okay, so I can perhaps mention it here itself. Since this forms a collection a cover for E, uh, I see that curly in, I had earlier defined curly ij to be the collection of all net intervals at the level j. So this is same as curly ij. And that's something I can compute, and we have already computed this is 3 per minus j per s times 2 per j, and that's equal to 1. Yeah, so this way we have a lower bound for the s sum, or is it, yeah, the s sum over an arbitrary collection, curly j. Yeah. Any questions? You can give me the mic.
Yeah. So over there, you've said k is such that its length is greater than j and j prime.
That's right.
Are we guaranteed this, or are we picking j and j prime such that?
No, we are guaranteed this.
For I mean, in the illustration you
Since I'm
made,
choosing j and j prime to be, let's see, what is the requirement I need?
I actually wanted to ask as well. When you
Yes.
say largest, do you mean one of them is the largest possible, and then you just pick another, or
No, both of them are the largest possible in the
Uh,
sense that you cannot have, like, I cannot find if j and j prime are are the pair that I'm choosing, then I cannot find a parent of j contained inside I. I cannot find a parent of j prime contained inside I.
okay? So they need not be. I mean, they will be.
So both of them
Okay.
are largest in their chain of.
Okay, understood. Right.
Yeah.
Yes, understood. Okay, sure. And so why are we guaranteed that k is larger than both of them?
Let's see.
Oh, okay. So j prime is in a different. So
Yes,
j prime is contained inside the other interval in the level of j.
that's right.
Therefore, k contains at
Yes,
least the middle third,
exactly. That's right.
and
Yes.
therefore it has length bigger than j, and in turn j.
Yeah,
Okay.
yeah,
Okay. Sorry.
yeah. That's
Thank
okay.
you.
Yeah. So it's possible that the endpoint of j is a bit far from the endpoint of j prime. Yeah, I think we should wrap it up soon, right? Yes.
Yeah. So yeah. As I understood,
Is it on? The mic?
I think it's on.
Yeah, it's on. It's on. Yeah.
Yeah. So even to get that, the final collection that I get covers the Cantor set, we need this maximality assumption, right?
Sorry.
To get this that this in covers the covers the full layer,
Yes.
we need this maximality assumption, right? Because I mean, we are not covering the same amount that we initially do when we can get this j and j prime. But because they are maximal, if there is some part that I finally don't cover, then I can sort of look at why I didn't cover that and get a contradiction because.
I mean, see, yes. So it's you need it to be maximal so that I can write down I in this fashion. Like if
Okay.
I were choosing j and j prime to be this collection, say,
Right.
then clearly I cannot be written down as a union of these two guys. I mean, sorry, that's not true. I mean, like, you can. I mean, even here I am basically chopping off one
Yeah.
piece of I.
Yeah.
But the point is that you're right. It won't cover the
Yeah, unless
that's
you
right.
take
It
the
won't
maximum.
cover E. Yeah. Yeah. So maximality is needed for that.
Okay.
You're right.
So and also this minimality here we don't actually use, right? This is just to to
That's
start the
for a
exercise.
choice actually. I
Okay.
mean, so that you can
Yeah.
yeah.
Okay. Thanks.
Yeah. Thank you. Thank you. No, day after tomorrow we have another session. Yes.